to vein dikes with regenerative mineral replacement, or RMR, of apatite from Grenville vein dikes at the Schickler occurrence, which is a vein dike locality in the Wilberforce area of Ontario. So just a little brief introduction about my project and goals. We're looking to investigate atypical fluorite-rich vein dikes in the Wilberforce area of Ontario. So this is not just the Schickler occurrence, but many vein dikes in the Wilberforce area. We want to evaluate the possible immiscibility of carbonate and halide melts and the resulting melt inclusions in apatite crystals, and examine micromineral inclusions and RMR within Schickler occurrence apatite crystals. So here's just an example of an apatite crystal on fluorite from the Schickler occurrence. So just to give some geographical background of where Wilberforce is, this is a figure by Ray McDougall from a Rocks and Minerals article, but here's the location of Bancroft, and then Wilberforce is just right over here. Zooming out a little bit, you can look at the location of the Great Lakes, and then the yellow pins that are labeled up here are the localities we're going to be looking at. Zooming in a little bit more, here's Bancroft, here's Wilberforce, and here are the localities. Again, here is the town of Wilberforce, and then we've got my 3 pins here for the localities. So if you're not quite familiar with what a vein dike is, it's an intrusion of carbonatite that's come up usually into silicate host rock. There's a dissolution reprecipitation going on with the host rock. This results in vein dike cores being made up mostly of calcite and apatite, while the margins of the vein dike are made up of silicate minerals reflective of the mineralogy of the host rock. Many collectors, as you guys are, know that vein dikes are known for producing very large mineral specimens. For example, this absolutely gigantic apatite crystal at the Canadian Museum of Nature. So why do we want to look at Wilberforce area vein dikes specifically? That's because Wilberforce area vein dikes, the cores of these structures are made up of segregated bands of calcite and fluorite. Now, it's not super unusual for vein dikes to have the presence of fluorite, but the sheer volume of fluorite in the Wilberforce area in these vein dikes is absolutely crazy and exceptional. So here we have this lighter colored mineralization in the vein dike core is the calcite, with the darker portion, almost black looking, very, very deep purple fluorite. This is very coarsely mineralized at the Schickler occurrence, but if we look at examples from the nearby Richardson or Fission mine, the vein dike core has a more sugary texture in terms of the calcite and fluorite. You can also note flow textures around these apatite crystals in the vein dike cores. So I've collected samples on site at the Schickler occurrence. I then embedded these apatite crystals in epoxy resin to create pucks, which I then polished and stuck in the SEM for analysis with X-ray energy dispersive spectroscopy. So I've done a lot of backscattered electron imaging, EDS spot analysis for chemistry, as well as EDS mapping of areas of interest. So let's start off our conversation with RMR, or regenerative mineral replacement. So what is RMR? This basically occurs when a mineral undergoes dissolution and reprecipitation to replace itself as the same mineral. You may have heard John Rakoven refer to this before as pseudomorphism, because we have one mineral replacing itself as the same mineral. This is a figure from a Dan Harloff paper, basically showing what RMR is. An example of fluorapatite that has been experimentally reacted with HCl to cause metasomatism. So the apatite that has been altered is the darker color in BSE imaging, and the unreacted apatite is the brighter color. So as I was looking at Schickler occurrence apatite crystals, sorry for that, we noticed that we have lamellae of higher BSE intensity that are inclusion poor, and lamellae of lower BSE intensity that are inclusion rich. So those are these lamellae in the apatite crystal here. Also note one of our melt inclusions that we're going to talk about later in reference to where the lamellae are. So I wanted to learn more about these lamellae, so I did some EDS maps to look at elemental distributions. So here is an SEM BSE image of some of the lamellae in a circular occurrence apatite. Notice how all of the micro-inclusions are seemingly concentrated within these bands of lower BSE intensity, and all of the areas of higher BSE intensity are relatively inclusion-free. So here we have EDS maps of phosphorus and calcium as two of the main constituents of apatite, as well as various REEs. So if we look at the darker intensity lamellae here, that corresponds to this in the phosphorus, here in the calcium, here in neodymium, going forward with cerium and lanthanum. So we notice opposite trends in element distribution with phosphorus and calcium and with neodymium, cerium, and lanthanum. The areas or the lamellae with lower BSE intensity show an increase in the color in the phosphorus and calcium maps, while there is less brightness in those colors for phosphorus and calcium in the areas of the apatite that have a higher BSE intensity lamellae. The opposite is true with the REEs. So in the lamellae of lower BSE intensity, where we have all of these inclusion phases, we see less neodymium, cerium, lanthanum in the main body of that band of the lamellae, but all of those elements can be found concentrated in those micro-inclusion phases. So this points to possible RMR happening with these samples. So we have dissolution reprecipitation of the apatite, and all of the REEs and other fun things that were running around in the apatite structure, garbage can, then did not go back into the apatite structure when it was reprecipitated, and instead have gone into forming their own micro-inclusion phases. So that's why we see these trends in the distribution of phosphorus, calcium, and the REEs in this apatite. So what are some of these typical micro-inclusions that we see in the circular occurrence apatite that have resulted from regenerative mineral replacement? Like I said, a lot of these are rare earth phases. And here is a typical EDS spectrum from an analysis of one of these inclusions. You can see the rare earths that are present in this spectrum. All of the minerals that are found as daughter phases within melt inclusions, which we're going to talk about in a few slides here, are also represented in the micro-inclusion assemblage, but other minerals are also present. So these minerals include things like thorite, uraninite, pyrite, some hematite, rare earth carbonates like bastnasite Ce, other rare earth minerals, also some yttrium phases, lots of things like that. Okay. So when we look at circular occurrence apatite crystals, we also notice that they are distinctly very red or reddish brown in color when compared to apatite crystals from the nearby Fission mine or also Dwyer mine being more distinctly green in color. So we think that the reddish color in these apatites is due to hematite, and we think this is likely sourced from alteration fluids, not from the apatite itself during the RMR process. So in addition to the RMR process happening with fluids coming in and causing alteration to the apatite, we have additional fluids coming in to bring in iron to form the hematite. And hematite is usually precipitated along fractures, like these fractures in this example here. So now let's talk about some of my work with the melt inclusions in apatite crystals. This includes not only the circular occurrence apatite, but also apatite from the Dwyer mine. So here's an example of macro scale melt inclusions within apatite crystals from the Wilberforce area. So here is an about 1 centimeter, really, really big example of a fluorite melt inclusion next to a smaller calcite melt inclusion. This is an apatite from the Dwyer mine showing a large fluorite melt inclusion, and also over here, it's kind of hard to see, but there is a calcite melt inclusion. We identify these as melt inclusions, mostly based on their globular morphology and also the texture of daughter phases seen in SEM imaging, which we're going to look at now. So here are some examples of backscattered imaging in SEM of melt inclusions in apatite crystals. So we see both monomineralic examples of melt inclusions of calcite in this example here, and fluorite in this example here. And we also see polyphase examples in the other inclusions picture. In these polyphase melt inclusions of both fluorite dominant mineralogy and calcite dominant mineralogy, we have additional phases like thorite, uraninite, pyrite, hematite, bastnasite CE, other rare earth phases, including yttrium phases, and also some quartz. We also have examples of mixed trapping of melt and solid phases, which is exemplified by this inclusion here. So we have quartz that was trapped as a solid while this fluorite melt was trapped as a liquid phase. And we can tell that based on these reentrant angles in between the boundary of the melt inclusion and the quartz crystal. And also a lot of times when we have mixed trapping, some of these more solid phases when they were trapped exhibit faceting. Another thing to note here is this example of calcite and fluorite present together within the same melt inclusion. We can see that the calcite and fluorite, while they're present together in the same melt inclusion, the two minerals are distinctly separated from each other instead of being mixed together. Now, this combined with the banded nature or separated bands in the calcite and fluorite vein dike cores at these localities suggests to us that we have immiscible liquids. So just to continue on with some examples of melt inclusions, we have a light microscopy image of our best fluorite melt inclusion along with the backscattered electron view. And you can see this interesting darkening of the fluorite around the thorite, and that is due to the radioactivity of thorite. You can also see the globular nature of some of these daughter phases inside the melt inclusion itself. Here's that other example of mixed trapping of the quartz crystals along with the fluorite melt inclusion. There's an example of it also in a light microscopy image, and some of this orange coloration along the margin is due to the hematite. So just to leave you with some conclusions from my work in this presentation, we have the presence of a carbonate halide melt that was or became heterogeneous and immiscible. And we based this conclusion on the distinct separation of fluorite and calcite within melt inclusions and also in the vein dike core. And there is variability in melt inclusion mineralogy, as well as the texture of daughter minerals within melt inclusions. We think that these deposits may represent the first example of a fluorite melt, which carbonatites themselves are very interesting due to the unique melt chemistry, but to have a fluorite melt seems to be something that's very important and very unique. We also have partial apatite alteration via dissolution and representation through the process of RMR involving late-stage hydrothermal fluids. We base this conclusion on the spatial correlation of microinclusions with lamellae of low BSE intensity. So this comes from all those EDS maps that I showed you. So my references. And that's basically it for my talk. So I'll take any questions, and my email